I want to talk a bit, as Anessa already mentioned today, about how data doesn't really lie, but can still mislead, and the kind of consequences that this can have on your machine learning applications, and what we can do to basically tackle those issues and how to ensure integrity of these applications. So just as a quick introduction about myself, if my slides want to cooperate, yes. So just a quick introduction. I sort of have a twofold career. So I sort of every week have two different hats on. So on the one hand, I'm an open source contributor, and in the past, I've contributed a lot to the NLP library that maybe some of you know, Spacey. And I'm currently also contributing to FastAPI and Typer, to other well-known Python packages that are fully open source and fully free. You can find my handle there as Sofie Van Landeghem. And sort of at the other end of the other hours of the day, I'm also a freelance consultant, where I basically work with companies who require NLP implementations or who have questions about how to integrate LLMs into their day-to-day operations and so on. And in this capacity, I am really sort of the data scientist, the machine learning engineer, and the business analyst all in once. So I have this one-woman company called Oxycoded, where I do this consultancy with. So these two lives are quite separate, even though I try to solidify them a little bit by trying to use open source methods and methodologies and models, open weight models, as much as I can into the consultancy work. But it's with this consultant hat on that I often think about data, and I often see data mistakes in projects, and this is kind of what has led me to making this presentation that I'll be sharing with you today. So let's say that we have a business client who comes to us and says that they want to create a portal, and they basically want to collect all of the Formula One news. So I'm a huge F1 fan, so it's a really good topic for me to talk about, and a sort of virtual business case that allows me to show you some real examples just in let's say, F1 sort of theme. So we want to collect all of these articles about F1, about Max Verstappen, who's been the world championship of the last years, but also the upcoming talents in McLaren, maybe even some articles about Lewis Hamilton, and so on and so forth. So let's say that we want to create this portal. And of course, once we have all of those articles, we also want to extract some facts from all of this news. So the portal should also be able to present you with some structured data that has been extracted from these news articles. So for instance, this year, we've seen quite a lot of different winners of the different stages of the Formula One races. It's been a very exciting year actually to watch the F1, because Piastri, who is currently leading the championship, has had some race wins. Verstappen has had some race wins, and so has Norris. So it's been, every week, it's sort of really interesting to see what will happen. And if you have this kind of article that says that Norris won in Monaco, then clearly, we want to be able to record that in our results table and say, well, okay, clearly Norris won the race in Monaco in May 2025. So let's say that we've created the system and we've extracted all of this data. And then one thing that I always advise my clients, and something that I always do myself as well, is just to go into the data and look at some example snippets, see what happened, and whether that all looks correct. Basically, do a quick quality analysis. Manually is one thing to do it. Of course, there's also various ways to do this systematically. But let's say we're just looking at this data for now manually. And we find this entry where it says that George Russell, who you see here on the pictures, has won the race in Spa, which is a circuit in Belgium, in July 2024. And we see all of these articles, pictures that clearly seem to support that Russell did indeed win this race. So it feels very natural to say that this is a correctly extracted fact. So I would say if all of you are looking at this and you maybe haven't looked at F1 races before, but seeing all of this evidence on the screen, I'm sure you would agree with me that, it looks like a correctly extracted fact, right? Well, unfortunately, no. So because what happened in July 2024, last year, in the Spa race, is actually that Russell ran a really brilliant race. He did win. He did finish first, let's say. But afterwards, basically after qualifying, there's always, after finishing the race, there's always various things that they need to check. So the F1 regulatory instances, they go and check the weight of Russell, the weight of the car, whether everything was in order. And in this particular race, what happened is that the weight of Russell's car was actually too low. So he had driven too long on the same tires, and he had lost some rubber on the tires, which meant in the end that his car had to be disqualified. So what happened in the end is actually Hamilton won the race because he was second. He finished he finished the line second. So he claimed victory after his teammate back then at Mercedes was disqualified. So in the end, there were some updates, of course, new news articles that have been published that rectified the fact and that said, well, in fact, it's Hamilton that goes and wins the Belgian Grand Prix last year. So what we see is that if you collect all of these articles, all of these news articles, you will have some conflicts in there, right? Some of the older articles will say that Russell actually won the Belgian Grand Prix. Some other articles will say that actually it was Hamilton that won it. And so we will have these different facts extracted. And what we'll need to do is, one, we will need to automatically first find the conflict. So this is something that we can very easily do with automated methods and see whether there's conflicts in the data, because clearly we cannot have two drivers on the first spot here. So we'll need to do some filtering automatically. And then you can go and say, well, Sophie, this is all very, simple enough. The NLP methods should be able to see that versus it was Russell who was first, and then he got disqualified. So Hamilton is the final winner. So this feels like a clear case where it should be very easy to disambiguate and see what happens here, and then clear up the data. But then, in fact, imagine my surprise when I was looking at this episode. So maybe some of you are familiar with this Netflix series that is shown every year. It's called Drive to Survive, and in this series they always talk about basically the last season. So in 2025, they're airing the season that is talking about what happened in the 2024 Formula One season. So just a few months ago, I looked at this episode that is called Looking Out for Number One in the Netflix series Drive to Survive. And they talk about this Spa race back in 2024. And they are basically telling about how George Russell is going to step up into a leadership role at Mercedes, because Hamilton is actually leaving from Mercedes. He's going to Ferrari. So they're talking about the Spa 2024 Grand Prix, and they're showing how Russell is doing a brilliant job managing the tires and being able to have one pit stop less. Basically, they show Russell on the podium and they say, this clearly shows how good a leader he is. He was now able to make these decisions and ended up on the podium. And they never, in the end, actually mention the disqualification. So the episode just ends saying that Russell is on the podium, Russell is first, and this is it. This is the end of the episode. So imagine my surprise, right? When I went to, or as some other user on Reddit accurately describes it, it's almost as if they pretended that George won Spa, which he clearly didn't. He did finish the finish line first, but he didn't win it in the end. So that is all just to say that even if you're looking at more recent data, because this episode was aired only a few months ago, the data might still be confusing. And there may be reasons why people obscure, who actually won it, or have some sort of storyline they want to adhere to, and then basically confuse the facts a little bit. So my number one sort of tip in these kind of data science or sort of AI projects is always to have a domain expert on board, somebody who's really into the domain, in this case Formula One, who will be able to have a gut feeling on what some of the data is and whether it's correct or not, and who will be able to do some of those sanity checks manually and just doing some quick checks there. So let's continue with our portal, and let's say that once we have all of these articles, we also want to be able to link out to Wikipedia. So what this means is that we're reading these articles, and maybe we want to know some additional information about the Spa Grand Prix or something like this. And an obvious feature that we can implement here is just to have a link out to Wikipedia articles, because there's so much information on Wikipedia. This seems like an obvious thing to do. So what that would look like is if we have the sentence that we all now know to be true, is that Hamilton actually won the Belgian Grand Prix in Spa in 2024 and not Russell. So in this case, for instance, we could link the word Hamilton to the official Wikipedia article that talks about this particular driver, and we could link the Belgian Grand Prix to this article about the Grand Prix that is held in Belgium every year. So this would really make it interesting for users to go ahead and read more information about these particular topics. But this is actually a quite difficult NLP task because there's a lot of Wikipedia articles and there's a lot of inherent ambiguity in words and so on. So this is actually a trickier sort of task than it might seem. It's called entity linking as an NLP task, and a lot of people have been working on this over the years. So this is something that we tried to solve as well some time ago, and this particular project is already a few years old. But let me walk you through it because I think it's quite interesting anyway, and the learnings are relevant to this day as well. So the way that we try to tackle this particular problem is to first collect some training data, and we can just get this for free from Wikipedia. So what we see here in the top, so in white, we see a sentence from the article about Lewis Hamilton, where it just says that this is a British racing driver who competes, and this year he competes for Ferrari. And so the words Ferrari are highlighted, as you can see, and they link through to another Wikipedia article. And the Wikipedia article that it links through is Scuderia Ferrari. So this is the team, the Formula One team, that is basically funded by Ferrari. Obviously, there are other Wikipedia articles about Ferrari, like about the actual car Ferrari, or other ways in which you can use the word Ferrari, of course. But as we can see from the sort of source code that is underlying to each Wikipedia article, we see there that the word Ferrari specifically links to this Scuderia Ferrari article. So these are kind of your gold standard links, right? Because what this tells us here as training data is, if we see the word Ferrari in this particular article about Lewis Hamilton, then it means Scuderia Ferrari. It means a Formula One team Ferrari. It doesn't mean the race, the car Ferrari or the brand Ferrari. So this is really helpful to mine all of these interwiki links and then go and see what the actual editors in Wikipedia did, and this will help train our entity linking model that we will try and design, basically. So the way that we built this entity linking model, and this is also why I said that this is already a few years old, because this is just using embeddings and neural networks, but no LLMs back in those days. But what we did was a relatively simple thing. We basically took the named entity recognition mention, so the mention from text where it says Ferrari, for instance, and we embedded that using a CNN. And at the same time, in the same sort of vector, we also embed the candidate article, so in this case, a Scuderia Ferrari article, and we basically put that all in one large vector. We run a neural network on top of it that will try and predict what the likelihood is that this sort of article is the correct one, given that specific mention in that specific article. And the probability will be between 0 and 1, and we can basically backpropagate that and compare it with the gold label that we harvested from all of those interwiki links that we collected earlier on. So we went ahead and trained this network, and I can talk about the details of this network for yet another hour, but I'll spare you. So let's say we just trained this network for some time, and at the end of this, we obtained 79% F-score. So initially, we were like 79% for a relatively difficult, NLP task is probably quite good, right? It's probably relatively good, right? At this point, we start being unsure. Is it actually good? 79%? We're still missing 21%. So let's take a little deep dive into that actual number, 79%. And what I've seen from experience when I talk to clients about these kind of percentages, whether it's accuracy or F1 or precision or recall, it doesn't really matter for most clients. Usually what they think is, well, 0 is out of the question, and 50% is sort of the first number that is relevant. And what they usually think is, if you do anything very stupid, if you just do random guessing, then we'll get 50%. And this is this is inherently untrue, but let me continue first with this slide. Obviously they think, well, the best model will obtain 100%, right? So let's get back to that 50%. A random baseline is never 50%. So I think most of you who are in this business know this. It's really only 50% if you're like throwing a dice and seeing whether it's an odd number or an even number. Other than that, it's almost never 50%. In fact, if you look at this entity linking task, if you think about a truly random baseline, so a truly random baseline would be, I'll just pick a random article from Wikipedia, which has about 7 million articles in English. So this is, it is virtually 0% at this point. If you pick 1 out of 7 million, we have kind of 0%. So the lower bound definitely is 0%, even though most clients already have a hard time believing this. And in fact, the upper bound in this particular case wasn't 100% either. So for efficiency reasons, we needed to keep all of the data in memory at this point to make it fast enough, which meant that we did sort of a clever pruning of the database. So as I already told you, there's a lot of Wikipedia articles, and we only kept 14% of them. Of course, we did this in a smart way. So we kept, let's say, the most frequently discussed concepts. So Wikipedia has all of these obscure pages as well, maybe about some, I don't know, some bug that has been seen once in some exotic country has its own page, which is really nice, but often enough this bug isn't mentioned in Formula One articles. So we just basically pruned the database a lot. And by keeping only 14% in this way, we were still able, some sort of Oracle disambiguation step, would still be able to obtain 84% F-score. So we thought that this was a reasonable trade-off, keeping the database quite small and in memory. But of course, it limits us a lot because it means that the modeling work at this point really targets 0 to 84% range. So even if we design the best entity linking model that we could, we would still only obtain 84%. So this is extremely important to sort of keep in mind and to know that that's really just the upper bound that we're working with. Okay, so let's revisit our percentage number. So I said before that we obtained 79%. And now we know that we're actually working against a range of 0 to 84%. So this means that 79% is really good, right? Michael on the slide is still a bit unsure, as you can see. And by now, you might realize that I'm sort of setting this up for being confusing as well, sort of on purpose. Because in this particular case, we really need to dig deeper. And another guideline that I would really give here is that you have to develop some simple baselines to better understand the complexity and the data challenges of your project. There's no other way to really understand what the 79% figure means. And this is what I will walk you through in the next few slides to really understand that 79% figure better. So in our case, when I said before, we can design a random baseline. Of course, we wouldn't be assigning the words Hamilton to any random page of the 7 million available ones on Wikipedia. We would do something slightly more clever than that. We would create a simple baseline by, for instance, just doing a lexical search of anything within Wikipedia that resembles the string Hamilton. So we will, of course, come up with our British race driver who's called Hamilton, but we will also get an article about Alexander Hamilton, who was a founding father of the US, also the musical, that was that is about this particular historical figure. And there's other pages as well that mention Hamilton. So we can just collect all of these candidates once we see this sort of string Hamilton, and then try and find the best one out of these. This is, of course, a much more clever thing to do, even though we might miss some candidates, but we can still see how well this particular baseline would do. So suppose that we would do this lexical search and then pick a random one from that candidate list, then we would already obtain 55% in F-score. So this is better than our 0%. It's a much better sort of lower baseline. And bear in mind that we're not doing any machine learning or NLP at all at this point. We're really just doing a very simple lexical search and a random selection. So something very stupid in a sense, but it's giving us a reasonable baseline to work against. And then we can improve upon that and see, well, is there a better baseline that we can create that gives us even better feeling of this data? So let me introduce you to the concept of prior probabilities. What this really means is that if you have a mention, such as, well, let's for instance say a mention is Obama, right? Even if I give you no lexical context, I give you no sentence or no other information at all, when I say Obama, I think everybody here in the audience thinks about the former president, right? So the former US president who was named Obama, even though I'm sure that there's very, very many more people called Obama. This is sort of what I mean by prior probabilities, because if you look at Wikipedia and all of the articles that are in Wikipedia, almost all of the mentions Obama will be linked to that page that is talking about the former US president. So this is sort of the weight of certain links. The same thing happens with our Hamilton case. Let's say, for instance, we are looking at these Formula One articles. well, then the textual mention Hamilton will most often link to this Formula One race driver. Let's say, just for argument's sake, that 75% of all of the cases link to this driver, maybe 7% mention really refer to the military officer, and another percentage, 10%, to the Duke of Hamilton, something like this. Of course, when the string literally says Lewis Hamilton, then the prior probability of this linking to the Formula One race driver will shoot up. It will be about 99%, something like this. Similar, if you have Alexander Hamilton mentioned in full, well, then it will probably be the US founding father, and so on. But what we can do, we can harvest these prior probabilities from Wikipedia. This is really just statistics, going through all of the Wikipedia articles, looking at all of the interwiki links, and seeing which kind of mentions are being linked to which kind of pages. We can have all of that data for free. And then the baseline that we'll do is we'll just basically round this up. So instead of 75%, we'll just say, well, if most often Hamilton is referring to the F1 race driver, then we'll just say, whenever it's Hamilton, we'll link it to the Formula One race driver. Whenever it says Lewis Hamilton, also race driver, whenever it says Alexander Hamilton, we'll link it to the founding father. So this is just a very easy way, and what I call sort of prior probabilities baseline, where we just exploit the sort of inherent connection that we make between certain words and certain concepts in real life. So the thing is, if we look at this prior probability baseline, we actually obtain 78.2% in F-score. And this is still not doing any machine learning at all. So bringing it back to the machine learning model that we trained earlier, which was using neural networks and sort of clever embeddings of the candidates and the named entities, that was supposed to disambiguate based on the context of the articles and all of the other words that appear in the article. That only obtained 79%. If we compare that to this very simple baseline of using prior probabilities, then we just have to conclude that the machine learning model really isn't learning all that much at all. And also remembering that there is an 84% sort of cutoff at sort of higher cutoff as well, it just means that there's very little room for the machine learning model to learn that kind of information. So why is this happening? This is really because the information on Wikipedia is very skewed towards these probabilities. When I said, when it says Obama, it will almost always link to the US president. And it's very difficult to learn from that 1% of cases that are not linking to that US president. So this is just an inherent property of the data that you need to take into consideration, maybe upweight some of those examples that are sort of going against the stream and these kind of things, and see how you can extrapolate that from a source like Wikipedia that is highly skewed to some other sort of information like the F1 articles, which will have a different distribution. So this was, I thought, a very interesting learning, sort of comparing this data to these baselines. And I would really recommend to just try and do a stupid thing first, create a simple baseline, because it helps you, on the one hand, understand your data better and see what kind of biases and distributions are in your data. And at the same time, once you start training models, you will also be able to put their performance into the right perspective. So there's one other thing that I want to sort of come back to here. So let's revisit that upper bound again. Imagine that we would have no memory or efficiency requirements, and we would just be able to keep the entire database, maybe in memory or some other way. Then the question becomes, is it really 100%? Is the upper bound really 100% if we have no requirements? Because what does 100% accuracy really means? It means that everything you predict is entirely correct. And then we get a little bit into sort of a philosophical part of the presentation, because what does it mean to be correct? If every disambiguation is correct, what does that really even mean? And let me give you an example. So we have here, again, the same sentence: Hamilton won the Belgian Grand Prix in Spa in 2024. And the word Spa can be, in this case, they can be disambiguated to, let's say, two candidates, two different Wikipedia articles. One article is about the circuit of Spa-Francorchamps. So this is the F1 racing circuit, and it lies in the city of Spa, which we see on the right-hand side. So this is another article. There's an article about the city of Spa, which is in the southern part of Belgium. So the question here becomes, should we normalize the word Spa to the circuit, which is informally referred to as Spa, or should we normalize it to the city of Spa, which is the actual location where this circuit is located in? In fact, maybe we can do like a quick, on the chat, maybe we can do like a quick vote. So who would think that on the one hand side, let's say you just type 1 if you think this should be disambiguated to the circuit of Spa, and type 2 if you think that this should be disambiguated to the city of Spa. Anybody who wants to risk a vote? No wrong answers, I promise. And no peeking with what somebody else types. So we have a few 1s and a few 2s. So that's usually what happens. And I would actually say that in this particular case, there really are no wrong answers, because it happened in Spa, on the circuit of Spa, but also in the location Spa, in the city of Spa. They're both kind of correct. It just depends on how you would analyze a sentence. And it also depends a little bit on your personal preference. What would be the article that you would want to read if you would click on this word Spa in Wikipedia? Let's actually do a few more. I think I have 2 more where we'll just try and see what everybody thinks about this disambiguation. So here's another sentence where it reads, societies in the ancient civilizations of Greece and Rome preferred small families. There's 2 ways in which we can disambiguate Greece. So on the one hand, we have ancient Greece, talking about, you know, the ancient civilization between the several centuries ago. Or on the other hand, we have the current country Greece, the country in Europe as it is today. So what does everybody feel like this should disambiguate to? 1, it would be ancient Greece, and 2 would be the current country Greece. Let's see, some 1s. So I think, if I'm not mistaken, everybody votes 1 on this one. Yeah, maybe. So I might actually disagree a little bit, because it says ancient civilizations of Greece, which to me kind of reads like ancient civilizations, sort of ancient versions of the current Greece. But it really depends on how you read it, because if you're just interested in the sort of history behind it, then you want to click through and read about ancient Greece. It depends on whether you're sort of reading this semantically or grammatically, I think. Okay, let's do 1 more, the final one. So here it says full metro systems are in operation in Paris, Lyon, and Marseille. So we have 2 ways of linking Marseille to a Wikipedia article. Either we link through to the actual page that exists about, in detail, talks about the Marseille metro, or we link it through to the city Marseille, that is a city in France. So what does everybody think? 1 being the detailed article about the Marseille metro, and 2 being the city of Marseille. Cast your vote. So I see some 2s. And I think there's a 1 from William as well. Yeah, cool. Ah, sorry, a 2 from William. Your 1 was from the previous vote. Yeah, perfect. Okay, so there is some agreement in the room here, and basically you typically, what I gather from these 3 examples is that you typically want to read about the more detailed article that the sentence talks about as a whole. But if you're an NLP system and it reads here, full metro systems are in operation in Paris, Lyon, and Marseille, what you would, I think, what most NLP systems would read is that Paris, Lyon, and Marseille are 3 cities in which there are metro systems. So they would probably label Paris, Lyon, and Marseille as a city. And as such, it's likely that they would actually disambiguate Marseille to the city article, because sort of the grammatical interpretation of this. Anyway, it's interesting to see what different annotators think about it and how you would label that, because that is really what you need to do when you're developing this kind of portal and you want to have these link outs. You need to get a feel of what it is that people want to link through to. It's not just how the NLP would interpret it or what the actual grammar would say about this, but you really need to have a feel of what the users want as well. So typically what you would do here is you would assign multiple annotators to label the same data samples as we've just done here. I think we had about 10 annotators sort of in parallel labeling these data samples and looking at how often they agree. And this is what we call inter-annotator agreements, or IAA. And this is a super interesting value to have. It's not always easy because you need to have enough annotators that really understand the domain and understand the application that you want to develop and so on. But if you have high inter-annotator agreement, then you're really golden. The gold data is reliable and robust, and you're basically setting yourself up for success, and your application is built on solid grounds. The problems happen when you get low inter-annotator agreement. I think we had lower annotator agreement on the first example. And basically what happens there is the annotators agree, and you need to figure out why. Maybe the data is confusing, maybe the label scheme is ambiguous, maybe the NLP task is too complex, and there's just too many sort of decision points to take for the annotators, and they just it's just difficult to get to the same result, basically. So to give you another example of that, where this was a particular use case that we ran with a client, where we had to label articles according to a specific ontology, and where we also had multiple annotators doing the same sort of exercise and comparing the results. So what happened here is that the user or the client basically gave me this ontology. It wasn't this particular ontology, it was a slightly different domain, but I can't show you the actual details, so we'll stick with the F1 team. So they gave me this ontology and then the news articles that we had to label. And they wanted to label exactly what, so they wanted to attach exactly one label to each news article. So we started labeling some of this. We did a manual labeling exercise. We created an annotation framework for this client, and we had some of their own people labeling the data and putting basically going through all of this manually for some, I just think, a few days. And then afterwards, we plotted all of the data. And what we did here, so we plotted the sort of, well, for lack of a better word, let's call it confusion matrix. It's not really a confusion matrix. But what we see here is if you have a 1 on the diagonal, for instance, with traveling, there's a 1 on the diagonal, which means that everybody who labeled something traveling, all of the other annotators agree, and there was no confusion at all. But we do see in this matrix some places where there is, in fact, some confusion. So these are excellent opportunities to go and see what is happening with the data. So for instance, somewhat surprisingly, we saw a confusion happening between global politics and US politics. So you would think that mostly you would be able to say whether something is about US politics specifically or global politics. But I can sort of imagine that, sorry, I was slightly confused with the slides here. So in this particular case, there might be some events in the last half a year that have happened where some US politics have influenced global politics in some way. I wouldn't exactly know how. But if this is the case and you see this happening in your data, you could consider merging the labels, especially if it's not relevant for your application. If you're thinking about sports articles and you just need to know whether it's basically something else, it's just maybe something politics, and if humans can't reliably distinguish them, then it's fine. You can basically just merge the labels. So this is something that we try to convince our clients of, not to see the ontology as sort of something that is fixed, but actually go through the data and go through the use case and see whether we need to make some adjustments. Similarly, we saw confusion between US politics and Formula One. This is also this is even more surprising, let's say, than the previous one, because why would one annotator label an article with US politics and the other label it with F1? So just go and look at the data and see which articles are underlying this sort of confusion. And for instance, we find this kind of article like this one, where it basically says that the team bosses of the different Formula One teams are looking at, what is happening with the international tariffs and so on, and they're unsure how to, proceed in terms of budgets and so on. So the problem here is not that it's very unclear. Actually, both labels are relevant to this article. F1 and US politics are both relevant. But what happened here is that the client really was insisting on labeling just one label for each news article. And even though we had said beforehand that this is probably not the best idea, they could only be convinced once that we showed them some of these articles and once we showed them the confusion that was happening between the annotators, because that also meant that the data just wouldn't be stable and reliable enough. So from this point onwards, when we were able to show some of these cases, we decided to just allow multiple correct labels for each of the articles. This can, in fact, also increase some of the confusion or some of the conflict between annotators, because now they can pick multiple labels. But as you can see, it's just really required for the task here, because otherwise it doesn't make any sense to pick between either of the two. And this is something that we also see a lot in projects, is that we just need to reframe the task to match the data. Often clients come in with sort of preconfined idea of how the NLP task should look like. And I think that this is kind of the wrong way to go about it. What you really need to do is first look at the data, look at how things should be annotated ideally, and what it is that your application needs downstream, and then design the correct NLP task to solve it. The final kind of confusion that we saw was within the sports category. There was a lot of disagreements there. And this is an actual, so you might be thinking that I'm sort of exaggerating here, but this is based on an actual project that happened exactly like this. So there was a root category called sports, and then there was a subcategory in another category that was also called sports. And so one would have all of the different sports and the other wouldn't. So it really here depended on which one caught the eye of the annotator first. If they saw 3B sports, then they would just annotate it with that particular label, and they wouldn't consider all of the subcategories anymore. So this is just inherent ambiguity in the label scheme or in the ontology that needs to be addressed, and that can pop up in these kind of qualitative exercises that you do having multiple annotators. So that's just a good exercise to go through, basically. So just as a sort of general tip, I would definitely say, together with the domain experts, critically revise the label scheme. You might be saying, well, that's all fine and dandy, but what if you don't have multiple annotators? I know that a lot of projects currently don't have access to all of these domain experts, which cost a lot of money and time. So clearly that's a concern. But if you don't have multiple annotators, let's say you just have, you don't even have one. Let's say you have 0 annotators. What you can still do is analyze the discrepancies between your model and the predictions that it makes and the gold standard label. So in fact, this is a case, so we saw some of these example sentences before, but this was a sentence that came up when I was doing this evaluation. So I didn't have multiple annotators at the time, but I did have the model's prediction and the gold annotator. So here the sentence talks about a certain person, Agnes Maria, who died in 1201, and she was Queen of France. So the gold annotation on Wikipedia here, France, is linked to the current country, France, in Western Europe. But the actual prediction that the machine learning model made, this entity linking algorithm made, was to a page that also exists on Wikipedia about the Kingdom of France in the Middle Ages. And if you look at the dates, this is actually completely correct. So the date 1201 seems to fit perfectly in this historical period where this particular Kingdom of France with those kind of borders existed. So judging from the crowd online today, I think I think that most of you will also want to read about this Kingdom of France in the Middle Ages, if you're reading this article about Agnes Maria, who was a queen of France back in the day. So when I looked at this, and I'm always a huge advocate for my machine learning models, I'm like, they try to do their best. They look at all of the data, they make a prediction. If it's said to be wrong, or if it's judged to be an incorrect prediction, I typically want to know why, and I'm always sort of sympathetic to the model if it makes mistakes. In this particular case, I would really say it's debatable whether or not this is a correct or incorrect prediction, right? So when we just count all of the false positives and false negatives in the data set, this would count as a false positive. Or maybe the label is wrongly annotated, and maybe both answers can be seen as correct. This is also a sort of solution that you could bring and say, well, maybe there's not one single correct answer. If it's a article that is relevant and the users would be happy to go and read on about that particular article, then maybe they're both correct. So this is a sort of vague answer to this philosophical question that we had earlier, to say, well, what is correctness really? And I think we often shouldn't be as black or white in our sort of evaluations. In fact, this is a figure that I produced just a few months ago in a report for a client, where I was calculating the precision of a particular machine learning method that we had designed for them. And I basically said, well, okay, there's some cases that are clearly correct, most of them. There's also some cases that are clearly incorrect, the yellow ones, not so many. Then there's some cases where I'm unsure because I cannot even decide because there's just not enough context. So those are probably data points that we need to remove from the data set. And then there's some cases that I called related. So the ones in green, where I said, well, if you're not being very stringent, then they are, in fact, they could be correct predictions, or at least close enough. So depending on the use case that you have downstream and the precision that you really need in your application, or how exactly you will use those predictions, I would say the precision is about 87 to 96%. And to be honest, I don't think that I would have ever done this like 20 years ago when I was just starting my career. But right now, I'm sort of starting to embrace the feeling of ambiguity a little bit, and sort of embracing the fact that correctness is not always as clearly defined. The other thing that is really interesting to do is to look at wrong predictions on the training data set. So this might be surprising to you when I say run predictions on the training data set, because that's not usually what you do. You usually predict an unseen data set, but it's a very neat trick to basically find structural data errors. And let me give you a quick example. So we had a manual training data set in a project that basically looked like this. There were some sentences, and we were annotating the entities in the sentence. In this particular case, we're annotating the names of races on the Formula One calendar. So, for instance, Dutch Grand Prix is annotated as an entity, and Monaco, where there's also a famous race, is also annotated. So this is a training data set. We run the machine learning model on it. It was obtaining very high scores. And then we predict the entities again on the training data set. So of course, at that point, we remove the annotations. We just take the sentences as such, the raw sentences, run them through the prediction algorithm. And in this particular case, the last sentence actually had the Monaco GP, so those two words, annotated as entity. So you can see that the boundary of the entity is different than what is in the original sentence. Again, that's surprising because usually what happens is that the machine learning algorithm is quite able to remember cases from the training data set. But at the same time, the machine learning algorithm also tries to, or the model also tries to find general rules. And what happens here is that the annotation of the Grand Prix names wasn't done consistently. In the first sentence, we see that Grand Prix is added to the name, while in the second sentence, GP is left out of the annotation. So this basically brought us a realization that, well, we should really be consistent in this. Either we include all of the words Grand Prix or GP into the annotation, or we don't. And we can have a very similar thing, for instance, when we're annotating school names or city names, these kind of things. And what happens here is it's really important to write up these kind of annotation guidelines. If you're lucky enough to have human annotators doing all of this manual work for you, just help them be consistent in their annotations by writing up very clear cases, giving them very specific rules, what they should do in these kind of ambiguous cases. It will really help your data set being more consistent and robust. And your machine learning algorithm will thank you because it will be easier to find these general rules. And finally, correctness may really also depend on the downstream usage of your results. So if you look back at this example that I gave in the beginning of this sort of philosophical talk about what is correct, should we resolve spot to the circuit or to the city? Well, if the only goal of this particular case is to just find which Grand Prix was being run, what Grand Prix is being talked about in that particular sentence, then both of them would probably lead to the correct result downstream. So it really depends what your end goal is and whether or not you will be able to get there. So just as a sort of a generic recommendation, it's really important to climb the right hill. And this is something that I always try to keep in mind. Climbing the right hill means thinking about your data. Is it correct, consistent, and robust? And I always think back about the Wikipedia data, which was very skewed. Was that really representative of the real world application that we wanted to use the data for? And does your evaluation capture the value of your algorithm in production? And that all of those sentences or questions should help you think about, am I climbing the right hill when I'm looking at these accuracy numbers, and do they reflect my progress correctly? It's only after we defined that right hill to climb that we can get to the actual fun stuff, being the algorithm development, model training, LLM fine-tuning, and so on and so forth, that every machine learning engineer loves to do. But I still think that it's very important to think about the hill first. So just to end the presentation, I want to wrap up with basically a practical checklist of things that you can or should do in a machine learning project. So first off, about the data annotation. it's super important to ensure that your label scheme is consistent and ambiguous. And if you're doing annotation, then definitely draft these clear annotation guidelines to ensure data consistency. If, again, you're lucky enough to have multiple annotators, then definitely measure inter-annotator agreements and plot some analyses with this data to try and find ambiguous cases in your data and see what they mean. If the inter-annotator agreement is low, definitely consider reframing your task, checking the ontology and then making some adjustments there. And also, if you can, you probably want to model some uncertainty in your annotation workflow. So for instance, just allowing an annotator to say that they're uncertain about a specific annotation can already help, rather than forcing them into a black or white decision. With respect to performance evaluation, as we saw in the beginning of the talk, definitely develop some simple baselines to put performance into perspective. And if you can, try to quantify the upper and lower bounds of the specific task that you're working on. And then, of course, measure your performance as part of the larger business problem and not just a single F1 measure. And finally, identify structural data errors by predicting on the training data set. Of course, this is just a sort of research exercise. This doesn't tell you anything about how good your model will be in practice. For this, you still need to apply it to unseen data and make sure that you're climbing the right hill before you do any of the modeling. I know this has been a long presentation, so if there's really just only one main takeaway, it's that Hamilton won the Belgian 24 Grand Prix and not Russell, as Netflix has said. Thank you for your attention, and I think this is a QR code to my LinkedIn page. If anybody's interested to connect, I'd love to. And yeah, happy to answer any questions that you have as well.
Thank you, Sofie. This was a very insightful presentation, and also it was fun to put on the hat of an ML engineer and think for a moment I would label the data. And now I remember who won that Grand Prix. Everyone in the audience, if you have any questions for Sofie, you can use audio or put them in the chat.
I have a question about, so that first kind of like Oracle disambiguation that had that 84% upper bound. Could you go into a little more detail about how you calculated that upper bound?
Yeah, so that was really, so what happened there is that we had to cut entries out of the knowledge base. So instead of keeping all of Wikipedia articles, we just kept 14%. And so the Oracle disambiguation then just means if we have a mention in the text, we will just see whether it's still in that database or not. You see, so it's really just checking. Oracle just means that it will be able to find it if it's there. It will be able to disambiguate to it if it's in the database. That's just what I mean by an Oracle disambiguation. So it meant that by keeping only 14% of the entries in the database, we were still able to cover 84% of all of the mentions in our data set.
Gotcha. Okay, that makes sense. Thank you.
Hi, Sofie. I have a question about multiple annotators. If you have multiple annotators, one of the values you get is the discovery of the ambiguity or the disagreement. If you train them, do you produce artificial agreement and give up some of that value?
Yes, you do, but you should train them in the way that you think benefits your downstream application most, right? So for instance, if we're thinking back about those cases about, the Paris metro system or the ancient Greece, if we say, well, we always want to have the more detailed article because that's what our users will be interested to click through, and you put that as a guideline into the annotation guidelines, and yes, your annotators will be sort of biased towards that guideline, and they will start doing that. But then that just means that you're capturing the value that you want your application to have, right? So I think that's a good thing. No?
I don't know. I wondered whether there are cases when you want to do what you just described and you're effectively injecting a bias based on your downstream interpretation, or if you want, on the other hand, to capture something that is more crowdsourced from those annotators instead of injecting your own view.
Yeah, I mean, so what you could do is run the annotation effort first and basically see what comes out of it without too many guidance, but that does take an additional sort of iteration loop, which means a lot more time and effort. But that will help you capture sort of the wisdom of the crowd without steering them too much. And you can also do a similar thing after you've built the application and once you put it in production and try and somehow find user feedback, basically. And if it appears that the user feedback is completely different than what you trained your annotators on or what you trained your model on, you could also try and revise that. So it's definitely a little bit going back and forth. So I'm a huge fan of this sort of iterative loop, create data, create models, but then have a feedback, and maybe you'll have to go back and iterate on your data and your models. I think that's often inevitable. So yeah, but it's an interesting question to think about, definitely.
Thank you.
We have have time just enough for 2 more questions. So if you have questions, please use audio or put them in the chat. I have a question, Sofie. In this presentation, you covered more philosophical questions and the strategy and so on, but I'm from a practical perspective, what tools do you prefer to use?
Oh, it really depends. I'm not the kind of machine learning engineer who gets hung up on specific tools. In terms of data annotation, for instance, it really depends whether the client already has some methodologies in house, or we can design something for them. In terms of model building, it's also I can't give you a clear answer. Like 5 years ago, we would be building neural nets. These days, we would be building solutions on top of LLMs, preferably open source. In my case, like open weights LLMs. But it really depends on what your client needs. And this is something. It's actually an interesting, I think, sort of evolution that a lot of ML engineers are seeing in the domain. Is that clients often come in and say, we want an LLM because LLMs are talk of the town the last 2 years, and then they give this example project, and I'm like, this is just supervised machine learning with a model that can run on a CPU, and we can probably get to like 98% accuracy. And this is the kind of conversation that I like to have with clients as well. Like, do you really need 99% accuracy on this huge GPU infrastructure where you need a lot of money just to get it online? Or is 98% equally well in the downstream? So yeah, I try to find the correct solution for the project. Really, it's it depends is always my answer. Sorry.
That's often the best answer, the most accurate answer.
It is, but also the least helpful. But yeah.
All right. Well, one last call. If you have any questions, please ask now. And if you think of questions later, please post them on LinkedIn in our group. But for now, this is all for today, for this month. Sofie, thank you again for this presentation. And to our attendees, thank you for all being here, for your curiosity, for helping to shape this thoughtful discussion. And we'll be posting the presentation on the OpenTeams YouTube channel soon. If you missed anything or just want to revisit the highlights from today's presentation, keep an eye on your inbox. And if you'd like to keep the conversation going or start a few new ones, please join the LinkedIn group. And with that, I'll stop the recording.